Okay, so we start our second section. So I tried to find WTA and WSS, but I didn't find their the abbreviation word. So later on, you find out, then let you know. But the important issue is that one is not critical. So you have to know the pitch prediction in time domain and frequency domain. What's the big difference? Most of them is from the waveform behavior. One is time domain, just try to find the waveform similarity, try to calculate correlation. In spectrum domain, they also can do the correlation. They also consider like a synthetic approach, try to make a good use some approximation. So, however, they are combined pitch prediction from time domain and frequency domain. We can do the good job together. Do the good job together, work them together can get a good job over there. So the other one, we are talking about the center clip. So we try to make sure we are remove some not important part. So maybe we can get a reliable or good performance here. So the other issue we have to focus because our pitch, our pitch is the main idea is your gratis vibration. So during a short term, your vibration do not have a big change. So this one, your pitch is related to your gratis vibration. So during the short term, short term is not a big change. No big change. No big change. No big change related to your vibration frequency. So your vibration, the trigger signal during a very short period, not so big change. So your pitch a little bit neighboring friend. So the pitch signal. So neighboring friend. So neighboring friend the pitch. So you have a many speech friend. You have a many speech friend here. So neighboring friend or speech friend, you can see their pitch, the tau 1 and tau 2 and tau 3 uh, could be not big changes. So they will be a little bit different, but they are not big change over there. So we can base on the pitch tracking. Maybe we are assume their voice area, the pitch should be a little bit consistent, not a big change. So like this one, we can one is like a code forward pitch is a frame zero. So we find the best pitch will be tau zero. So later on, we are not from the 16 point to search to the 160 sample. No, we are not searching that kind of region. We only search related to your tau zero, just 1.2 tau zero and 0.8 tau zero. Around this kind of range, you try to find the best match pitch. And then later on, we got a winner, the tau 1, and then we try to find the next winner. According tau 1 is 1.2 tau 1 and 0.8 tau 1 around this range. So we minimize the search range, sometimes make their pitch the variation a little bit consistent. But this one just working for a voice speech frame. If they are related to voice, sometimes could be not consistent. So they have a pitch tracking, so they have some region, so you can define alpha will be what kind of dynamic range you want to search. The other one is a forward. One is a forward, the other is a backward. So you can according forward and backward search to define your range. So this one not big deal. This one just give you idea. They have different approach, try to find reliable pitch. But we are according the physical phenomena. The human being, the gratis could not change too much. So they have some consistent the variation will be a little bit change is not a have big change over your pitch. So during your voice frame. So during your voice frame. So during your voice frame, so then when the pitch change, it should be a little bit not big difference. So a little bit consistent. So we can limit your search range. Sometimes will be limit some noise. So you can limit, make sure you did not find a double pitch or pitch of a half a pitch. So avoid that kind of area so we can limit the search range. So we know the big difference for your pitch detection. So cause the error sometimes is on voice frame because on voice frame, if you are doing the pitch prediction, there's not make sense. And sometimes the onset, onset and offset speech frame. Sometimes onset is indicate from the voice from your speech frame. Onset in the beginning no speech smaller and later on. So this one is the onset. Offset offset is like we have a speech and later on no speech. So this one we call the offset. So offset. So according to this kind of speech frame, we are trying to find the pitch. So it's not a little bit make a little bit big variation. The other one, if you are speech frame, this one most of them are voice. They are voice frame. So they are voice frame. Supposed to be their pitch tau 1, tau 2, tau 3. They are a little bit different, but it's not a big change because our gratis, because it's not a, according your so physiologist, it's not easy human being to do the big change. So this one, so you keep in mind, so we can base on our pitch variation of behavior, so we can minimize the search area and also can avoid double pitch, half a pitch, the some pitch prediction error come out. So later on in your textbook, they're talking about a lot of different approaches. So it's too many details. Okay. Okay. So they try to conclude this section. So you can see here, almost all the pitch detection algorithms have a peak detector, so decide the pitch by the peak position. So in time domain, the peak is detect not only position at correct pitch lag, but sometimes will be multiple. So it's double pitch. So real pitch is so once you find the peak point, your cost function, normal autocorrelation, you find the maximum value. Sometimes you'll be divided by 2 to make sure is there any second one. Two-step, pick the maximum pick and double check your submultiple position. Submultiple, so submultiple position to see there is a comparable pick. However, since there is no fixed solution to this problem, so close correlation pitch relationships. So sometimes we are looking into you find a pitch, so you try to find that kind of pitch divided by 2. Half a pitch is any dominant value. That one is dominant. Could be you find a double tau, so you have to be double pitch. So you have to make sure is any the other potential real pitch over there. So they just tell you how to avoid double pitch. For frequency, you find a winner in frequency domain. So you try to divide small fundamental frequency and make sure you are not find two fundamental frequency. So they just the other way try to make your pitch prediction more reliable. So in this first section, they're talking about pitch prediction. So pitch prediction related to your gratis vibration. So we can consider in time domain and frequency domain to do it. So more reliable, they are combined them together, or many pitch predictor combine them together can get a more reliable performance. Also, if you have a pre-processing, sometimes can contribute good result. So this one, in the textbook, they propose the center clip. So they are center clip, or if you have an LPC coefficient, you also can do the LPC inverse filter to remove LPC and make sure you remove the envelope shape so you can more remaining signal more related the pitch information. So another one you can consider because you have pre-processing. Also, you can try to think about is it possible because pitch variation during the voice frame they are consistent. It's not a big change. So we can define some because if we find the first winner and later on the neighboring speech friend, next neighboring speech friend, so we can consider plus 20%, minus 20%, that kind of range to do the search for pitch. So we can minimize, we find out the double pitch, half of pitch, the issue over there. And so on, they can be forward and backward pitch tracker. So try to minimize, try to find the pitch more reliable. The final one in your textbook, they just say, if you find a winner in time domain, maybe you can double check half of pitch. Do we maybe it's not a maximum one. Maybe they are second winner. Maybe they are relative around the 0.9 ratio of the maximum. So maybe they are the really pitch data is not a double pitch. If you are in the frequency domain, you find a fundamental frequency. Also, you can double check that frequency divided by 2. Maybe we find a double fundamental frequency and double check your cost function over there. If the value is occupy some amount, so that value is a little bit, maybe it's not best one, the big one, could be the second one, could be is a relative dominant one. So you have to be careful to make sure you are not find the double fundamental frequency. 值不会变异很大，只要你第一个音框抓的是可靠的，那之后是不是 pitch 呢？是根据第一个音框的 pitch 加20%减20%，那的范围去做搜寻，这样的话你就不会第二个音框找到的是2倍的 pitch 或1半的 pitch， 因为你只加20%啊。那你可以 forward， 就是说前面来做后面的预估，也可以从未来再往现在来做预估啊。你因为后面你也可以先用 pitch 的预估来 refine 你所有 pitch 的位置啊。那其次的课本最后的结语呢是说，当你找到的时域轴的方式找到的 pitch， 你可以在那个 pitch 时域轴的 pitch 的位置除以1半，去看这个的依照你的 autocorrelation 的 cost function， 就假设是什么样的 cost function， 它所算出来的值对应你现阶段的最大的 winner， 这个 winner 它的那个 cost function 的值 如果它也是蛮 dominant，就是或许它不是第一，它也是第二或第三，这时候你要考虑是不是它会是正确的 winner。那如果你在 frequency domain 找到 winner 的 fundamental frequency 的话，你也应该要去 make sure 你不会是找到2倍的频率或3倍的频率啊。那所以说你要除半那个频率除半去看你的 cost function 是不是也是有一个重要的值啊，合理有某种程度大小的值，比如说这个值占你原来的 cost function 0.9，所以说也是蛮大的成分，所以你要小心不要找到2倍频。Okay, this one is our section 6, what we're talking about the pitch prediction. And the last section, they are talking about voice on voice classification. So the voice on voice classification is more like if we are doing the speech encoding, if we know our speech waveform, if we know speech waveform, no voice, like if we know the speech waveform, no voice here. So like this one, we are partitioning many speech friends. So you can see here, so this one we are called the offset from the voice to unvoiced. So this speech friend, they are a half of onset. One is onset. So this speech friend, they are from the voice to including the voice to unvoiced. So this one from the unvoiced to voice, so onset. The other one we call the voice friend. So this one is unvoiced friend, also unvoiced friend. So right now we are trying to determine how to determine your voice friend or unvoiced friend. So most of them, they are based on with a simple way. So in time domain, we can use in the correlation. So this one, because pitch signal, they have some correlation. So if we find the pitch, so we can say they are according to the pitch, we calculate their normal autocorrelation. So we can find some value is bigger one. So this one you can see if we are this is speech waveform. So we are trying to calculate if we know the waveform, the pitch. So according to your pitch, we calculate normal autocorrelation. So we can see the value bigger the threshold is like a voice area, and smaller than your threshold is like unvoiced. So you can see here because if you have a pitch information, you calculate the pitch for each speech frame. So for each speech frame, you calculate the pitch first. You calculate your pitch first, and then according their pitch. So you can see on voice frame we also calculate their pitch. So according to this pitch, we calculate the normal autocorrelation. The value becomes lower. So we can pass on because if we are using the voice region, their pitch autocorrelation according to your pitch moving, so they have a high value. So we can, because the speech signal they have a harmonic, they have some harmonic signal. So we can based on that kind of information try to calculate some cost function like a normal autocorrelation based on your pitch, based on your discover pitch value. So that one value will be voice friend. You can get a higher autocorrelation value. Non-voice friend, it will be the lower autocorrelation value. Another one, they are using the picnics. So you can see we are trying to using the square and also amplitude. So because they are voice signal, the voice signal they have a high amplitude, high amplitude. So your voice signal have a high volume. You have a high volume. You have high volume. So because you have a high volume, so because on voice the signal more like a noise. So this one you take a square. If you have a high volume, you take a square and then the maximize the value over there. So your summation your speech frame, many value, you high value, you take a square and summation and uh, take a take square root again, so the value becomes bigger. So you can see if we have a voice signal here, so you can see that one will be make it bigger. On voice signal, the value will become smaller. The other one is simple way, is called zero crossing. Zero crossing is inverse because we have speech signal is not frequently cross zero zero. So on voice signal, so more like noise, their signal is a high frequency cross the zero. So you can see we can use in the easy way neighboring data do the multiply. So one is a positive, the other is negative. So supposed to be they multiply together become the negative value. So that one can become 1. So you can see your speech frame, a lot of crossover the zero value. So you'll be looked at more like a noise. So this one is very straightforward because your speech signal or the waveform is a little bit like they have a waveform shape. So this kind of shape is not frequently close to your zero. So that one we can make good use. Try to indicate which frame is a voice, which frame is unvoiced. Another one they call the spectrum tier. Because in the previous section we are talking about short-term prediction. Because neighboring sample, speech frame neighboring sample, the amplitude is close. The neighboring sample, the amplitude they are close. So we are trying to using their first their first order normal autocorrelation. So their neighboring signal do the multiply and divided by their energy. So you can see our speech frame they have a neighboring signal correlation. So it will be high correlation, but the noise neighboring signal do not have a correlation. So their value will be lower. So another one is a pre-emphasized energy ratio. So you can see our neighboring signal do the subtraction. So because they are similar, neighboring signal subtraction normalize their energy. So you can see our neighboring signal have a similarity. So their subtraction normalize there will be lower value. So however, if you are noise here, so neighboring signal subtraction will be higher. So will be because you divide your scale your amplitude, so they are not similar. So you have to do the subtraction, so they will be make the value become bigger relative to their original amplitude. So another one is the low band and full band energy. So because voice speech signal have a higher low frequency energy, so we are considered like a first kilohertz. Below first kilohertz, the energy band versus the whole band over there. Whole band is a 4 kilohertz because we are sampling rate is 8 kilohertz. So because you are a speech frame, most of the energy occur happen at a low frequency band. But if you are noise signal, sometimes a high frequency. So you can see speech signal have a low frequency, so most of the energy. So you can see we are for here low frequency band energy over your whole frequency band. So you can see the ratio become bigger. So the other one, frame energy. So we are consider how to calculate the frame energy will be this one. We have many criteria. So the other one will be consider using the energy. Voice speech signal have a higher energy than on voice. So we can use in the consider their energy. However, we have to determine what's the energy will be, what kind of energy treat as voice, what kind of energy we are determined to be on voice. So they are trying to define the threshold. So one threshold they call E maximum. The other threshold they call the E minimum. So if you are coming speech friends, the energy are bigger than their E maximum. So they will be including this E0 to become their E maximum. So incremental update their E maximum. Otherwise, so their E0, so they will be also a little bit affect your E maximum. So you can see your alpha will be 0.5. So if it's bigger, E0 bigger than your E maximum, so your E maximum will be biased by E0. So if your E0 not bigger than your E maximum, so E0 did not bias too much because your gamma is 0.98. So we'll be trying to keep original E maxima a little bit. But this one coming is a low energy. However, will be bias your E maxima do not play big impact. So another one is the low bound. So your coming energy become your previous friend low bound criteria lower. So you have to pour your low bound more. So the tau could be 0.55. And if the energy is bigger than your previous friend, the low bound E minimum, so we have to pull it up, but the pull it up is not so big impact. So they 1 minus 0.98, so multiply 0.02. So we are trying to, if we are bigger our E maxima, we'll be pull up E maxima quickly. If we are smaller than our E minima, we'll be pulled down more quickly. However, if you are value smaller than our E maxima, our E maxima criteria will be affected by current input, but the impact will be lower, only 0.02. So will be affected a little. And if your data energy are smaller than our criteria E minima, so they are bigger than our E minima. So you are trying to pour up, make our E minima bigger, so that value is pour out will be little bit 0 multiplied 0.02. Also, you also have to define E average according your current input energy. Like take 1/4, another one third of a quarter, third of a fourth. So multiply a previous average become new average. So this one, if you are coming signal plus the threshold bigger than E maxima, and you're coming bigger than E average, so we treat this one as a voice. If you are coming smaller than your E minimum plus threshold 2, we are treat them on voice. Otherwise, we are not sure right now is a voice or unvoiced. So you can see this figure, they show you the upper bound. This one is your upper bound, E maxima. This one is your E minima. In between is your E average. So you can see the dot line, the dotted line is a friend energy, your friend energy. So you can base on this kind of criteria and to determine which part are voiced, which part are unvoiced. So you can see if we are bigger, almost bigger our averages, so they look like we are voiced here, and bottom here will be unvoiced, and later on you can see we are voiced here. And decision making, so we are talking about so many voice on voice determination method. So the other issue is how maybe we can combine them together. The critical issue is how to determine the threshold. So sometimes if we are combining them together, maybe we give them the weighting value. So become final to determine this speech friend is a voice and unvoiced. But right now, it's not like a pitch because the pitch we can from the frequency domain and time domain. They have a little bit limitation by their phenomena, physical phenomena. So we can compensate their pros and cons, and then get a good their advantage and disadvantage, and try to get a good performance. But this one, voice on voice, is not hard to say which one is reliable and which one is non-reliable. Most of them depend on your signal behavior. Sometimes you are in the noise environment. Sometimes some close zero could be good because your background have another noise. So that one is difficult to say which one is good, which one is bad. But however, you can combine them together. Combine them together to see the performance. So another one is soft decision. It's not a hot decision. What's the soft decision? Because we are using voice on voice, so it's based on your speech friend. This speech friend we call the voice, and this friend we call the voice. This one is an offset, depend on your skin, what kind of skin you are using. Could be the voice. So each harmonic we can define voice on voice. So if we can define voice on voice, so each harmonic we can define voice on voice. So we can define their voice or on voice. So this one we call the sub decision. So maybe I'm using the bigger one, bigger capture, bigger information. So we have in the past we are in time domain, so we are partition many speech friend. So this one we can say is voice. So just one, and then in frequency domain they could be like this one. So we are partition many harmonic. So each harmonic. So this one is a voice. Could be this one. Could be this one is voice, and this one is on voice, and unvoiced, and so on. So some of frequency band on voice, some frequency band is a voice. So they call this one is a multiple band excitation method. So in frequency domain, we can determine a multiple according your frequency band, the frequency band based on your fundamental frequency, according your fundamental frequency to determine many frequency band. Some frequency band become the voice, some frequency band is unvoiced. So it's not this one we call the mixed voice unvoiced. So we are not focused on this area because this one is based on frequency domain. So we are not talking about here. So you can see they try to calculate this one. They have a frequency domain. So this one just give you some idea. We are not talking about frequency domain. So we quickly bypass here. So this one is not our focus. Multiple band excitation. Because we are not talking about multiple band. Okay, so I'm using the Mandarin to repeat the voice on voice in this section. 好，那这一章节呢蛮简单的哈。那我们重点是说一开始呢，他说我的音到底我要怎么去判断有声跟无声？好，音框，因为我们是如果我在做压缩，我要知道我的音框到底是有声还是无声啊？那有声的时候我才做压缩，无声的时候我是不是就用一个 indicator bit 就可以传到对方了？我就不用再去浪费很多的 bit 去做压缩。那基本上的压缩技巧，课本提到的是说，你可以因为语音有一些周期的相似性的现象，就是有 pitch。那如果我的音框已经找到 pitch 的话，我就可以把它的那个什么 normalize 的，就是 winner 的 pitch 点，算出它的 normalize 的一个什么，它会得到一个 normalize 的 auto correction。相对的，有声的时候 normalize auto correction 会高，无声的时候 normalize auto correction 会低。那另外一个呢，就是说，我们有声的时候，实际上的能量都比较大。我把能量大的平方相加，再开根号，相对应的能量低的相加开根号除以原来的绝对值的能量，相对的有能量大的会值，最后的值会大。那所以说某种程度是侦测它的 peak 点，所以你可以发觉有声的时候，它的这个相对值会大，相对值会大。那 zero crossing 呢，就相对很 straightforward， 就相邻的点，如果是刚好在零附近，有一下变正，一下变负，一下变负变正。那因为有声的时候，它的那个 embouchure 是某种程度的连续性，不会正负一直变，频率没那么高。无声的时候，正负变频率会高，所以我就看正负变的频率会高，高的就可能那个音框就会是无声。那另外一个呢，这个是算是相邻的时域轴的讯号有 correlation， 它不会能量，因为这个就是我们的 short term prediction， 不然我的 short term prediction LPC 就不能做，因为它的下一个讯号可以用前面的讯号做线性组合猜出来。那也就是说，它有周围的讯号有 correlation。那有声的时候 correlation 会高，无声的时候 correlation 会低。那相对的就可以用这样去算出一个大小的差异。那其次的话是能量的 ratio， 也就是相邻的讯号有相似性，我可以相减，那就会把它变小，相对变小。那人类的声音比较是低频的能量是有一定成分的大小。如果我们把说话的时候的低频的能量对应它整个 4K 的全频谱的能量，应该占的比例会高。无声的时候大概是比较偏因为它乐理率高，频率也相对会偏高一般来说。那其次的话，我也可以设计一个以能量 energy 的角度来看，所以我定义了 E maxima 和 E minima 的条件，也就是说我现在的音框代表前面所有音框所算出来的 E maxima， 我现在的能量比之前的 Emaxima criteria 大，我就要把前面的 Emaxima 尽量往上调。那所以说就会用0.5，也就往上调的速度快。那有时候我说话整个音呢有点慢慢都变弱了，那这时候往下调的速度要变慢。那 E minima 呢往下调的速度要快，往上调的速度要慢。那 average 呢，它实际上某种程度就是后面还占1/4，前面占3/4，也就代表说 average 比较很快的 track， 比较快 track 你的 local 的特性。那借由再做一些组合，既然你还要定一些threshold 1、threshold 2，那一些条件你可以定有声跟无声的关系。那最后在决定声音的时候，你可以考虑它们之间你要决定这些threshold，你可以做组合式的那至于说谁好谁不好，要看音的特性不像前面讲 pitch 的时候很明确时域轴大概是对。时域轴是对长周期，也就是说男生较长的周期的效果会好。频率轴是对短周期，短周期的话，短的 pitch 就代表较大的 fundamental frequency 效果会好。那这时候我就可以把2个方法做组合会得到一个合理的结果。那前面所讲的都是 half decision。half decision 的意思是说，我就是针对一个音框，它就是有声，就是无声。你即使是 onset offset 呢，我也是把你当成就看你的有声的成分有占多少，成分越大 dominant 就可能是有声。offset 的话，如果看情况谁的 dominant 比较大，有可能判断成无声，就看情况。那另外一个呢，就是说我根本不是这样看，我是看的是说我的声音呢，把你音框呢转到 frequency domain， 我的 coding 呢是在 frequency domain。那我 coding 既然在 frequency domain 的话，它的精神就是说，我的有声无声呢是根据我的 fundamental frequency 切出来的 frequency band。根据你的 fundamental frequency 切出来很多的 frequency band， 那在这么多的 frequency band 里面，每个 frequency band 都可以决定有声无声。那这样的话，就变成是说你有 multiple 的决定，而不是单一决定类似是这样。那有利于音的效果。那这个在这种 multi-band excitation 在频率 domain 的方式去判断有声无声是有帮助的那这是在其他的频率 domain 的 coding 会用。那我们这些强调的是比较是时域轴，所以我们比较不会去探讨，所以后面这些很细的东西我们就不需要去探讨它了，考试也不会考。Okay, so in this chapter, we are summarize here. We are focused on almost like we are not focused soft decision. Soft decision is based on multiple band excitation. So that one is based on our frequency domain, and then we find out the fundamental frequency. So we partition your frequency domain into many fundamental frequency bands. According each fundamental frequency band, so we can determine that frequency band is a voice on voice. So it's not one speech frame. We are not determining half decision for one speech frame like a voice on voice. So one speech frame transferred to the frequency domain, we give them many voice on voice indicator. That indicator is based on fundamental frequency band. So we are partition. Many fundamental frequency band. So this one bandwidth is f0. So we partition many fundamental frequency band. For each fundamental frequency band, we are consider your energy. Your energy is sufficient large of our threshold or some criteria. We determine your fundamental frequency band is a voice. So you can see if we partition 10 fundamental frequency, so you have a 10 frag to indicate for each one, indicate they are voice or unvoiced. So this one we call the sub-decision. So sub-decision is not a one indicator, one frag. So in our final, we are not looking into in detail here. This one just another approach. Okay. So I summarize here. In this chapter, we are talking about pitch prediction, accurate pitch estimation, and also we're talking about the voice-on-voice classification. So sometimes we consider multi-domain, like a combined frequency and time domain to do the pitch estimation. Or they can get a good performance even under the noise condition. However, some complex pitch estimation algorithm maybe not perfect, but in some pitch are not well defined, some error inevitable. So you can see the pitch estimation performance right now most overall performance in the speech encoder, most of them, well, pitch prediction sometimes is okay. Depend on how to use it, how to use different approach. Most of them, they are based on time domain because they try to reduce the complexity. So they are, but however, they based on some mechanism try to avoid double pitch prediction or triple pitch prediction. They're using some mechanism. So that one is a little bit reliable and also it's good performance. Another issue is a voice on voice. So it's very straightforward. So easy way you can use in the zero closing rate. That one is a low complexity. So that one, most of them, they are using the zero closing rate. But however, how to determine the threshold, that one is another issue here. So you have to think about how to determine the threshold, or you can base on some criteria adaptive from your signal to determine the threshold. But in this chapter, they did not comment on that. So in addition to half decision, the other one they call the sub-decision or multiple decision inside a speech frame. So multiple decision, so they are based on frequency domain. So according inside the frequency domain, we are based on your fundamental frequency band, and then according multiple frequency band, each frequency band we are determining they are voice or unvoiced. It is voice or unvoiced. So they have a multiple flag over there, multiple indicator to related to one speech frame. So the codest one is not half decision. Okay, so we are last one. We already talking about the short-term prediction. You know, we have a speech frame, so we have a short-term prediction. Short-term prediction is trying to do the LPC, and also we are talking about the pitch. So it's a long-term prediction. Long-term prediction. This one is a short-term prediction. Short-term prediction is like a LPC prediction. So later on, we know in the previous section we're talking about if you are LPC inverse. So yours is remaining signal. What's the remaining signal? What's the remaining signal? So we have to model that one. What is the remaining signal? We have to model it. We have to model it. So this one is the last section we have to work it out. So this section, chapter 7, we are talking about analysis and synthesis. So first one, we are not a perfect reconstruct original signal. We are consider mean opinion scope. So top quality, we are consider mean opinion scope is bigger than or equal to 4. So we try to see, so this one, because you have an original signal. So we build up the model so we can do the synthesize our signal to double check our original signal to see the error, try to minimize our model. Why? Because you have original signal. You have original waveform, and then we are trying to window it, we doing the window. So we talking about how to do the windowing. Okay, so we have windowing. We have a windowing. So we do the windowing, and then we are using the Hamming window. So try to remove the boundary effect, and then we try to find LPC. So it's called a short-term prediction. So this one we try to do the quantization. We transfer to night spectrum pair coefficient to do the quantization. They have an intercorrelation and intracorrelation and make good use of their quantization scheme. And then we are trying to do the pitch. Try to find the pitch. So this one we call the long-term prediction. Long-term prediction. This one LPC, you are short-term prediction. Short-term prediction. So we have a pitch, what we're talking about the pitch, and later on the remaining signal, all this are model. So you can see analysis are based on, and later on we are called excitation. Later on, the remaining signal we are trying to how to do the excitation. So in your system, we have because we are do the encoder. Later on, you have a decoder. So if we are speech waveform, we have a speech waveform here. We have a speech waveform. We are doing an encoder and decoder. So decoder, we get a decoded signal. So we can get decoded signal. So we try to compare original signal, compare with original signal to make sure maybe we try to minimize, we try to minimize the distortion, How to minimize distortion? And then we try to minimize, because our speech waveform, we have developed encoder. Our encoder, we find some parameter. This parameter, right now we're talking about the short-term prediction parameter, LPC coefficient, and pitch coefficient. And then we have the other we call excitation. Later on we are talking about that. And then we have decoder, get a decoded signal. So because we have original signal, so we can have a feedback, go back feedback to do the comparison. Try to minimize distortion. So we minimize distortion, will be go back to optimize. Try to optimize your parameter. Try to update your parameter to make your decoded signal more closely or most similar original speech waveform. So you have a closed loop. So we call this one, this approach is called analysis by synthesis, because our decoder our encoder, including decoder, so they are synthesis. So analysis by synthesis. So we are by synthesis and go back. We have a feedback loop, and then pass on, try to minimize distortion, optimize our parameter. This one we call this one approach we call the analysis by synthesis. So you can see here. So you have an observed signal here, and then you have a system model here, and then synthesized signal. So you have an arrow. So we have an arrow here, and then we try to update our model, because update our model parameter, and go back to your synthesizer and try to do another synthesized signal, try to minimize their distortion. So this one we call the analysis by synthesis. So right now what we have an LPC coefficient, we have a pitch information during your encoder. So right now we another one we call excitation. So we can do the synthesize, and then later on we get an error. So we try to minimize here. So we can minimize our excitation signal. So maybe we do not do it here. We just do different last model. Last model, we try to optimize our final model. This final model is like an excitation. Try to find a good excitation, make them synthesize, can get more closely to original signal. Because this one is more like a model. This one is coding your signal waveform. But later on we do not have any physical meaning. We try from the signal behavior, we try to model the signal directly more like an excitation signal. So this one we are analysis by synthesis. We try to update our excitation generator. Decoder, because you get an excitation information and trigger duplicate according your pitch period and duplicate your information. So according your decoder, so you have an excitation signal. So according your decoder, so you have you have an excitation signal. Maybe I use a new one. According your decoder, like you have for one, you have a little bit excitation signal. So this like this one, and then you know your pitch. So you'll be duplicate according your pitch will be duplicate signal. You'll be duplicate signal. According your pitch will be duplicate signal. And LPC will be normalize all the information, and then also multiply your gain. So will be become original waveform. So this one is more like our synthesize operation. So you can see initialize. So what's the excitation here? So you can see this one is we already talking about here. So the first one, this one is our LPC, is a short-term prediction, short-term predictor. This one is our long-term predictor. And sometimes we talking about this one, we try to remove LPC. So you can see we find out LPC information here, and then we try to remove. So we define another in denominator. So you can see if your gamma becomes bigger, the value becomes close to 1 or smaller than smaller. So you can see we have another for different gamma according to W of Z. So you can generate more like an inverse LPC filter. So try to compensate their envelope shape. So you can see here, we try to determine our excitation. So gamma, most of them, they are using 0.8 to 0.9. So you can see original the waveform multiply our W of Z. So you can see they have become like this one, more like a reverse remove the LPC impact here. And also we are consider this one waiting. So the other one, critical part, we call the excitation signal. So excitation signal, because we cannot find any model behavior phenomena over there. So right now we are trying to, we can say is more like a brute force. Right now, what we do is more like a brute force to do the model. So simple way is like a couple excitation. So they are they are from the univariate stochastic sequence. So they are using define some code book here. So this one, they call the code book is a finite dimension. It must populate it, represented the excitation. So they are univariate. The code book design, they are univariate white Gaussian random number generate. They are not really from the source data. They are using the some univariate from the univariate, so it's more like a univariate to generate that signal. So univariate, white Gaussian random number, they are used. So you can see that one, they are trying to using all the other one Gaussian shape. So the remaining signal could be they have a Gaussian shape over there, and sometimes codebook they are using the center clip Gaussian vector. So maybe 1 and minus 1 to do it. So what's that? Because because we have original signal. We have original signal. So like this one, like this part. So you can see this one our original waveform. So we remove LPC, become like this one. We have removed the pitch signal. This one is our residual signal. So residual signal, we have to model it. We have to do the coding of them. So, but right now, if it's a speech frame, how big of a speech frame? So if we are 10 milliseconds, this one is your 10 milliseconds. So if you are 10 milliseconds, so it will be 80 sample. So this one, our speech frame is 80 sample. 80 sample. So right now you are remaining residual signal for excitation. So you'll be 80 sample. So how to do the comparison? How to do the generate your codebook? But they say this one is close like a Gaussian random number. So we are using the univariance. So they call it univariance. So univariance, the Gaussian signal, Gaussian number, Gaussian random number to generate what? Generate your covector, codebook excitation. So you generate the codebook. But this one, you call it 80, or maybe we are not using so many. So it's 80, you are do the mapping is so big. Sometimes will be downsample become the 40 to do the mapping, 40 to do the mapping, become the two friend, or we are mapping their up grid or even grid, depend on how to minimize the comparison. Sometimes we are consider their up grid or even grid to do the mapping, and then try to find which covector is best match the remaining signal. Sometimes we try to find the best match best match one. So because we are remaining signal, so like this one is around 80, around the 80 sample. So we call this signal is a closed univariate. We can use is a univariate. So this one we call this one is a univariate white Gaussian. Univariate white Gaussian random number distribution. This signal is a univariate white Gaussian distribution, more like a distribution, this kind of distribution. So we try to model the residual signal. So we are using univariate white Gaussian random generator to generate the covector. So the covector, this one could be how many you have? Could be like a 512 or 256 covector. So you have so many covector over there. So you have so many covector there. But how to generate a codebook? Very straightforward. They're using the univariate white Gaussian random generator to generate so many patterns. According this pattern, encoder and decoder using same pattern, same covector, same codebook, and to model the residual signal. So because speech frame is, for example, your speech frame is 10 milliseconds, so they are 80 samples. So they try to do the mapping. However, this one try to do the mapping, they take a lot of time. Could be we are consider because you are 80 sample. So if you are trying to index, it would be 0, 1, 2, 3, up to the 79. So we have 80 sample. So maybe we only consider even grid or odd grid. So maybe we just compare like 40, consider the 40. We are consider even 0 to 4, the index. So this index, the value. So we are consider this kind of index value. So this one is your index. So maybe we'll consider even index, or we consider odd index, make our vector become smaller. So sometimes we are not a univariate. Univariate could be the dynamic value, dynamic range will be -1 to -1. Or because they are could be 0.5, or the other one they call the unit. Center clip Gaussian vector. That one will be your vector just +1. This one covector. They can be 0.5, 0.2, or -0.2, and so on. The other one, center clip, they call the center clip covector. That covector only only 1, -1, 0, 1, 1, 1, 1. So center clip covector just 1. You only have 3 symbols: 0, 1, -1. Just three values to become the covector to do the mapping. So the mapping sometimes they have an excitation gain. They also have a gain. Before they are do the mapping excitation, they are unit gain, they are univariate white Gaussian to generate the codebook. And then sometimes the covector to mapping the residual signal, covector mapping your residual signal. So we can consider also multiply the gain and minimize your distortion and try to find which covector is best match. Sometimes we are trying to minimize your covector dimension. We can consider even grid or odd grid. We just compare even grid or odd grid, and then to find the best match. The other one we are omitted, so we are not considering. And the other one would be make your computation more easy. They call the center clip method. So your white unit, so their center clip, they call this one is your center. They call this one is center clip Gaussian vector, center clip Gaussian vector. This one, your covector just 0, 1, or -1. Only three simple. It's not a continuous mode from between -1 to 1. Okay, so this one is a codebook because we go through LPC and pitch. So your residual signal are more like more like a Gaussian, white Gaussian distribution. So we are based on white Gaussian distribution. We build out the code vector, codebook. So codebook could be based on your frame size. Sometimes can based on your up or even grid or based on your partition many subvector. So could be we can partition 4 subvector. So our codebook can be dimension become the 20, only 20 element, or only 20 element. So can based on subvector to do it. So make your covector mapping is easy. Covector mapping is easy. So because they are unit gain, so during our mapping we have to multiply your excitation gain. So the other one called one is distribution from your covector element distribution from -1 to 1. The other one is called unit center clip. So it's 0, 1, or -1. The other one, they're talking about self-excitation. So self-excitation, they indicate because our residual signal. So if we are coding, so this one, your first frame, so this one, your residual signal. During encoder, we have a residual signal in your encoder, and during your decoding, this first frame, and this one your second frame. So what's the self? What's the self method? Self method is based on previous excitation. We try to find this part is maybe copied from this part to here. We look forward which frame similar right now what we have, and then we copy them to here. So in the beginning, we can use white Gaussian distribution to generate in the beginning will be one-dimensional your excitation signal in encoder and decoder. Later on, you'll be try to search which part is more closely to like what we have the excitation signal. So they call the self-excitation. So you'll be based on past history. Your co-excitation function is there using structure similar like a pitch filter. But this one, it could be look like a second time long-term prediction. But this one, so it's based on, so it's more like a wrongness. So during decoder we get excitation. So we be because in the beginning you have a white Gaussian generate initial excitation signal, and later on we find out this area is a match. So this one will be concatenated here, but our previous one, this one will be truncated, and this part will be copied to here, become a new one for self-excitation. So for example, right now you try to do self-excitation. So current frame will be copied from here, and later on previous one will be truncated. This one will become cascaded in, become a new codebook to do the excitation. So this one is called the self-excitation. The other one we call the multiple pass and regular pass excitation. So this one is more like a regular pass. So what they want to do, because we have a 40, if you are frame size like a frame size is 40. Here, the frame size is 40. So your position grid, like you have a 1, 0 to 39. So this one your position grid. So if we are only we are trying to partition four combinations, so we are consider what's the grid here. So the position 0, position plus 4, 8, 12, and so on. So this one will be 36. And then second one is 1, 5, and 9, and 13. And this one is 2, 6, and 10, and 14, and this one will be 3, and 7, and 11, and 15. So it's 36, 37, 38, and 39. So you can see if you have frame size, our frame size is 40. Our frame size is 40. So we are partition, say, oh, we just from the 40 frame, because the frame, this one is our subframe. Our subframe is a subframe have a 40 sample. 40 sample, and according subframe, we try to find 4 passes. 4 passes, 4 signal. Only 4 signal will be modeled. So how to model this one? We are consider 0 to position 0, position 4, position 8 among this signal. So total will be 10 signal. According to 10 signal, which one is the bigger one? Which one is the larger one? Largest one. So if the largest one, winner is 12, that signal will be remembered. If for this one, some signal is a big one, so we keep this one. This one will be kept, and this one will be kept, more like this one. So you have this one is not good example, so they have a combination like a 10. So we only have a 4 passes signal. Try to trigger, try to model. And then you have a 10, so you have to pass on the 10 to find the winner. So during the coding, so this one is not good because 10 you have to using the 4-bit to do the coding. Because if you have a 8 combination, so you can using the 3-bit to coding. So what's this one is called a regular path excitation. So we have a subframe. So we have a 40 sample. I will recommend 40 sample. We are among them. We try to find four dominant paths. 4 dominant paths. But the 4 dominant paths, first pass will be from the 0, position 8, 4, position 8, up to position 36 to find the maximum one. And second pass, dominant one will be from the 1, 5, 9, 13, 37, find the dominant one. So this one we call the regular path excitation linear prediction coding. Another one, they call the multiple path. multiple path linear prediction coding. The other one they call the multiple path linear prediction coding. That one is based on because we have a 40 sample. Among them, we try to find 4 paths. So you have so many combination position. So many combination. Try to find from the 40 sample. From this 40 sample, try to find the dominant one. Try to find the dominant one. Could be positive or negative. Could be positive and negative. So they try to find the dominant one from the. So this one is a multiple path excitation. So we try to find 40 selected 4. So you have so many combination. So what do you want to coding? You'll be coding the position and coding the positive. Each path will be positive or negative, and also you have an excitation gain. That's it. So you have to code in. So multiple pass linear prediction. So they indicate a combination is more. So you have to code in your combination position. So the other one, each pass we have to remember they are positive or negative. And the other one is the excitation gain. Could be we have to give them the one gain or vector gain and make sure how to match original data. So did you got it? So this one is the most of excitation what we use. So first one, because we already go through linear prediction, we are go through linear prediction, short-term prediction, long-term prediction, and later on we are remaining signal. So this one remaining signal we try to model. So we are looking to this signal. They are more like a White-Gaussian distribution. So first one we using the codebook design. Codebook design we have a codebook design we can base on with codebook design we can base on White-Gauss univariance. We didn't know remaining signal gain. So we are design unity gain. So we design from the White-Gaussian generator to generate random generator generate some covector. This covector can be whole vector or subvector. And then encoder and decoder, they have using the same covector. So during your mapping, they try to each covector multiplied by gain, try to mapping your residual signal. Try to mapping your residual signal here, residual signal, original remaining residual signal from the pitch. So this one also your White-Gaussian we can use in the center click. So your covector just only three value, plus one, minus one, and 0. And the other one, univariance, this one is the value component. Each vector component from -1 to 1, they are continuous mode. So depend on your requirement. So the other one they call the SAP. SAP is look like we are design. In the beginning, we using White-Gaussian distribution, design one dimension, like a one-dimension covector, and then your is bigger than multiple frame size, and then coming speech frame try to find like a long-term prediction, like your pitch search. So they try to find which area distribution White-Gaussian noise White-Gaussian distribution more similar your current remaining signal, including the gap. They have a multiplied by gap here. So this one is similar. So they'll be copied to here and delete the one frame residual signal, become a new covector codebook here. So they are one-dimensional. One come in, you are look forward, and that one find a best match and copy in the cascading in the last, and the previous one will be deleted. So this one we call the SAP excitation. Another one, I don't care your signal is a White-Gaussian noise distribution or no White-Gaussian distribution. We are from your residual signal, from your residual signal, try to find the dominant one. So what's the mini dominant one? So if you are residual signal from the pitch, so we make it bigger. If we make it bigger, so we make it bigger. Okay. So suppose they are smaller. We make the bigger view. So bigger view. So this one is your speech frame. This one your speech frame. We from the speech frame try to find dominant value. So this one speech frame. So residual speech waveform. So we try to find a dominant value. So we only find like like your textbook just find 4 paths like this one. If you find the 4 paths, four, four, four value, 4 dominant value. So which one is the 4 dominant value? This one, this one, this one, this one. So we try to code this one. So if you are trying to code in this one, what do you need? You have to code in, because like for example here is a 40 select. So you have to know the position. This one you code in their position. You have to code in your 4 passes, the position among the 40 sample. And also you have to, your 4 passes, you have to know the positive value or negative. So you have to be, and then you also have a gain. So this pass, what's the gain? You have to code it. Could be unit one scalar gain, could be 1 scalar gain, or 1 scalar gain. So you can see we only have a 40 sample residue signals from the pitch. Remove the pitch information. Among them, we are not using the white Gaussian noise model to model. We just from this pitch residue signal to pick up 4, for example 4, could be 5, could be 6, 4 dominant signal. So 4 dominant signal. During our coding, we have to include the position. So you have a C40 selective 4, so many position. And then, so this one could be 2 power something. So this one is your number of bit you are using, during your encoding. So, and also each path could be positive and negative. So you have to give them a positive and negative. And also we are using 1 gain, could be 1 gain. So later on decoding, you'll be find 1 here. They are unit gain, not like here. So they will be using like recovered like this one. So this one they code this one is a multiple path MPLPC, multiple path linear prediction coding. So it's called a multiple path excitation. Another one they call regular path, because we try to select a 4 paths. We try to minimize coding so complicated, because we try to minimize this one. So they give some constraint. So first pass only occur. They only occur the position. They only occur the position of first pass. So first pass they only occur. What's that? So first pass they only occur 0, 4, 8, 12, 36. Second pass they only occur 1, 5, 9, 13, 37. So among them they try to find a winner. So later on, because they only have so many positions to do selection, so you can because this one is not good partition, because this one have 10 positions, so you have to use in the 4-bit. 2 power 4 bigger than 10. So you're using 4-bit to code in the position, 4-bit to code in the position, 4-bit to code in the position. And then each pass, so a coding original signal could be positive and negative. So we have to give them positive and negative, and also have a unity gain coding there. So this approach we call the regular path excitation. This one we call the multiple path excitation. So from the performance point of view, multiple path excitation have a better performance than regular path excitation because they are positioned more flexible. So this one is the main idea what we did, excitation. So if you have an excitation, so how to recover back? So you can see using the excitation for speech friend, for your speech friend, for each speech friend, you have speech friend, you have a pass here. So and multiply your gain, already multiply your gain, and then you have to know your pitch. So you have a pitch here, so you'll be duplicate according your pitch will be duplicate. So maybe the duplicate depend on how many. So you'll be duplicate over there. So it'll be duplicate. According duplicate, so you'll be using the LPC. LPC will be normalizing, and then also each one they have some gain over there. So you can see from the excitation. So we find the dominant one, and using your pitch will be repeat your pass. Or if you are from the code book, you have a many. If you are from the code book, you have a many small value, and then that one will be copied according your pitch will be copy many here. Copy later on the using LPC will be smooth then again become original waveform. So this one is our speech coding main idea here. Okay, I'm using the Mandarin to find out what we need right now. Sorry, later on this one is a final part we have to do. OK， 那最后有个比较重要就是 excitation 哈。那因为我们的 encoding 呢是主要的精神是用 analysis by synthesis， 因为我们是从原始讯号去做压缩。那原始讯号压缩就包含了你本来就是要压缩跟解压缩，就需要还原跟原来的讯号，如果能完全相似最好。那所以说，实际上我们的精神就是 analysis by synthesis 啊。那因为你已经知道你的 ground truth， 所以说呢，我们希望能跟原来。那也就是说，那我在 analysis by synthesis 的时候，最重要的就是说我要去 optimize 什么，也就是说我这个short term prediction 已经找到了。long term prediction 也找到了，正常来说，我就是最后这个 trigger 的讯号，我怎么去调整它，去比较能 match 原始的讯号，误差最少，越少越好。那这个 excitation signal 呢，精神怎么做呢？实际上呢，你如果去看呢 excitation， 它课本说，它那个讯号，实际上比较像是white Gaussian distribution， 那我可以用 code 的方式，那因为我剩下的还是一个 vector， 那我可以用 white Gaussian unit， 就是它的 gain 是1，然后我正建立了一个 unity gain 的 white Gaussian 的 vector， 那之后我在做配对的时候会乘上一个 gain， 找一个最佳的 gain， 那看哪个 covector mapping 的最好，那个 code 的 index 就是我的 coding。那我也避免要去算，因为它是 unity gain 啊，那所以说它的unit 应该算是 univariance， 所以说它的值是-1到1之间。那我为了减少计算量，那我也可以考虑是它的值只有正1、-1、0啊，它叫 center clip 去做 code 的配对。另外一个方法是 self 的方法呢，就是说我建立了这个比较像 code vector， 像是2维的。那 self 比较像是1维，就是说我只建立1维的FIFO， 有点像 FIFO first in first out， 也就是说我第一个就是整个1维的，那我长度当然大于好几个音框的大小，我进来的剩余信号在这个1维的讯号，当然它可能用 white Gaussian univariant white Gaussian 建构起来，它去做搜寻。因为我建2维的跟建1维的没什么太大差异啊，因为那我建1维呢，搜寻配对完到了之后，那个就会被我 copy 到我的原来的那个1维的就是后面，也就是说变成是 FIFO 就进来，那前面的那一个音框的资料就被我丢掉了， 所以说这样的话，我就把常用的 excitation 会被我留下来。那这是 SAP。那通常他们会说这个就有点像 second 第二次的 long term prediction， 一般有的时候效果不会那么好。那有很多的标准的用的是 multiple pass 跟 regular pass 的方式，也就是说，我居然剩下音框假设是40，课本是用40，那我这个40的 sample 呢，我从中间不要保留40，因为前面的 code 部啊 SAP 都是保留40，我能不能取比较重要的讯号？那课本是说我只要取4个重要的 pass， 那这个4个重要 pass 呢，实际上你就变成有 C40取4这么多位置的组合。那在这么多位置组合，所以说将来你在 coding 的时候呢，你就会遇到的一个问题，我的 coding 的时候，我就有这么多组合要去产生它的位置。那所以说呢，你就会变成 C40取4，C40取4这么多位置，所以说我中间会找4个 pass。那每个 pass 呢有正有负，所以你 coding 每个 pass 还有正负值。那接下来呢，你还要 coding 什么？因为我要乘上一个 gain。你刚才在我们做 code 部的时候，还做 SAP 的时候，原始的 code vector 就有正负了，所以我不用 coding 正负。我只要 coding gain， 因为它是 univariance 的 code vector， 或是 SAP 的一个一维的 code vector， 一维的 code 部。那所以说它本身就有正负了，但是呢，这个 multiple pass 呢没有正负，所以我将来会有要压缩的时候要告诉这4个重要的 pass 呢位置在哪里，位置的组合是在哪里，还有相对的正跟负这些 pass 顺序从左到右正负的关系，最后还有一个 unity gain。那4个 pass 实际上就看你的情况，越多 pass 当然保留越多重要的效果越好。那为了减少你去 coding C40取4，当然课本就会说我可以用一个规则性 regular pass。regular pass 的精神实际上就是说我原来的位置有一定的规则性，就好比说依照课本的例子，它有40个 sample， 我第一个 pass 只能出现在位置0、位置4、位置8，一直到位置36，第二个位置出现1、5、9、13，类似是这么多的位置，所以说我在这10个位置当中只选一个 winner， 他们当中最大值正面，也就是说代表我还是选出4个位置，但是这4个位置有一定的出现的规则性啊。那相对的，我在 coding 它的位置的组合的时候，虽然这个是10不好，一般都是2的乘幂会比较好，所以说要用4个 bit 就 coding 它的位置，4个 bit coding 它的位置是，所以说我代表multiple pass excitation， 那我必须要 regular pass excitation 呢，规则性的 excitation 通常的意思就是说我在 coding， 也就是在我剩余讯号，我只要找部分重要的讯号，然后部分重要讯号我就直接要抓你的位置，直接抓你的位置，然后在这个位置呢，我可能是有一定的规则，让我减少我的位置的复杂度。那一个呢是不管，就是从中间就选4个，或从中间就选5个，就看你的应用需求。Okay, so this one is the final critical one. We are trying to say a coding, speech coding. One is we are talking about short-term prediction. Another one is a long-term prediction. And later on, the final one is excitation. So excitation is based on analysis by synthesis. So we are trying to select which excitation signal goes through the pitch, goes through the short-term prediction filter, and to synthesize the speech waveform to see which one distortion is the minimized one. So it's a minimized one who could be the winner. So this one, analysis by synthesis. However, sometimes we have a residual signal. We can pass on residual signal to find the best match, and later on pass on analysis by synthesis to find the final best one. So you have to remember today what we're talking about. One is a pitch, how from the time domain and frequency domain. The other one is a voice on voice. So voice on voice is based on reduce your bit rate. If your speech frame is on voice, we do not spend any bit, or maybe just one indicator bit to indicate that is on voice. So that one will be reduce a lot of bit rate. So another one, the final one, we are called excitation. So the excitation signal, their behavior is more like a white Gaussian distribution. So they do not have any physical meaning right now. Maybe later on some guy say they have some physical meaning inside there. We can come out the model. But right now, most of them treat them like a white Gaussian distribution. So based on white Gaussian distribution, we are designed the codebook bags. So that one is a univariate codebook. Is each component inside the vector is between -1 and 1. So we can using the codebook match multiply by your gain, try to best match gain and try to minimize distortion and find which one is the best match. This one is covector best, codebook best. The other one called the set. So we can design one-dimensional FIFO, first in, first out. So it's more like a try to look forward, try to find which segment is the best match. That part will be copied to the left. The previous n sample will be removed. So final one they call them. We are not keep whole data. We are just keep some dominant signal. So maybe pick up some of the dominant signal like a 4 passes. We call the passes. So if for example 4 passes. So right now what we need to coding, we have to know the dominant pass position, the position. So for example in textbook, so the multiple pass excitation, they have their combination is a C40. Their combination is C40 select by 4. So many combinations. So we have to find out they are close to maybe like an n. So this one will be bigger than n-1. So this one, while we coding, we are using n-bit to encode. We are using n-bit to encode the position, encode the pass position, the position of the passes, encoding your passes position. So here, what we did, if you are multiple pass excitation, so we pick up some pass important part from then. So we have to know your pass position, and also we have to know your pass it will be positive or negative. So we have to coding each pass will be one bit indicate they are positive or negative. The other one is scalar gain. So later on we have an excitation signal. During the synthesis, we are based on excitation signal, and you according your pitch will be duplicate your excitation signal, and later on using linear prediction to smooth the original waveform come out. However, they also including the pitch gain. They also have a excitation gain and linear prediction and combine total. Sometimes they also consider energy gain, depend on your system. So most of them we have an LPC coefficient and pitch gain, pitch information, and pitch gain and excitation gain. So based on whole of information, so we can recover back original speech waveform. So that's our main idea. So you have to be well prepared our final exam. So I stop here, and our final exam will be next week. So according to these 2 chapters, chapter 7 we just highlight 1 or 2 sections, chapter 6, we are not give you tough question. Will be easy one because we try to finish it in this lecture just 1 week early. So we are final exam in this today lecture. We are not give you the maybe it's not a tough question. Could be easy problem for you to solve. So don't worry about that. So you have to be prepare our final exam. So now final exam is a closed book. So most of them is like a question and answer. So we try to find out physical meaning. And derivation will be simple one, not a complicated or equation derivation for you to do it on the final exam. So good luck. Okay, we stop here. Sorry, we are over time.